We've seen a lot of exponential models. We've talked about them in certain contexts too, and they work great for certain contexts, right? Generally, exponential models, we have to assume that there's, unlimited resources or a lack of resources, right? And there's no other interventions going on. And so they work great for a certain set of uh, conditions, right? In general, sometimes those conditions are difficult to achieve, and so we can't just always willy-nilly use an exponential model to fit a scenario, okay? In those cases, maybe we can adjust it a little bit. And if we adjust the exponential model a little bit, we get a variation known as the logistic function. And this actually pops up a lot of the time when you're working with populations and you're looking at changes in population behavior. Um, and so here, f of t would be, in these scenarios, more like your population value, okay? And then we get this c and 1 over, plus 1 over b e to the rt. Okay, we saw the e to the rt sort of happening in that continuous compounding case when we were talking about money, but we're talking generally about populations, okay? Um, so what are these here? Okay, the short answer is we'll get to those. But first I want to talk about c. C, in the context of populations, it's known as the carrying capacity, okay? And the idea of a carrying capacity is just the amount of stuff the environment or the context that you're in can support, okay? So when we're working in context of populations, it would be, what is the maximum population that you could have in of, whatever you're talking about, okay? So we acknowledge that populations can't exceed this without something in the environment breaking or killing off the populations, that sort of thing. Okay, so C is known as the carrying capacity, the maximum amount. Okay, B and R. Okay, B, I'm just going to leave this to say that this is a constant um, growth factor or constant change. I'm just say constant change factor. Okay, it is not our growth rate, constant change factor if I can write. Okay, and then R, this is just going to be a growth rate or a change rate. Okay, these are generally a little bit difficult to find without the use of calculus. So for now, we're just going to say if you need to know those values, we'll provide those. Okay, but the carrying capacity is one important concept that we um, need to look at. Okay, and so since this model is a little weird, I think it's a good idea if we just kind of see what it looks like. And if we look in Desmos, I just made a silly willy-nilly function, a logistic function here for us to look at. Okay, we see 10 is the value of C, 2 is that, change factor or change factor, and then we have a change constant, right, of 2 in here as well. And if we put those in, this is the sort of shape that we see. It's also known as a sigmoid function, or it's a sigmoidal shape. I think in part just because it looks like an S. But if you see also the term sigmoidal function, sigmoid, that is a logistic function, okay? But what we see when the logistic function is that it does exhibit exponential growth, right? At least in through here, and then it hits a point and it kind of stops being exponential and starts kind of plateauing, okay? And if you want to model that plateau behavior, that's where a logistic function comes in super handy, okay? So yeah, it grows quickly until a point, and then it kind of starts growing slowly and really doesn't change much after a certain point. That's when you're going to want to use the logistic function. And so if we look at an example where we're looking at the US population, okay, so I pulled census data and according to the US Census Department, they said in 1910 we had approximately 92 million people and a growth rate of 16.9%. Okay, later when we looked at 2020, the population was 331 million. Okay, and so we want to figure out the exponential model and then say, does it predict the 2020 population? So effectively, is it a good model, right? And then B, we'll look at a logistic model. Okay, so going through and doing the math now. The exponential model that we would get would be something like population is, the initial amount times 1 plus r to the t for time, or x, whatever you want to do, okay? And so what is A? A would be in the initial, okay. T years after 1910, so the initial amount in 1910 would be 92 million. Okay, so I'm just going to say that P is, just to be clear, population in millions. Okay, 92 times 1 plus, and then the R value would be the growth rate, so 16.9%. Okay, so just rewriting this whole thing, 92 times 1.169 to the t. And now if I look at the population in year 2020, that would be 110 years after 1910. And for this, I get 92 times 1.169 to the t. And if I put this in my calculator, I get 92 times 1.169, all raised to the 110 power. I get a very big number. So let's see, this is 26508433295. And then this would be million. Okay, so I don't think this is a good model. Okay, because what are we? This is a billion million, 2 billion million. Yeah, I don't know what kind of number that is, other than very large. Okay, so I'm going to say that an exponential model, no, this model does not work. Okay. So it was interesting to look at, but now let's look at the logistic model. So this one, I did the math for you and found that this is the best model according to the data. And so we want to analyze this function. Oops. And if we do that, we want to know what the carrying capacity is. And so that the carrying capacity is just this 671. So this is 671 million people. Okay, so according to this function, we're currently-ish at about half of the carrying capacity. Okay, so this is just our C value. Okay, and then now if we want to look at the population of 2050 under this model, okay, before I do that, I think it's just kind of interesting if we were to look at the function. So I found the model using some data. So I pulled the data from the U.S. Census, and here we have some of the data. Okay, and so now if I were to look at 2050, that would be 140 years after 1910. I'd be at let's see, 416 million or so. Okay, so again, we're not close to carrying capacity yet. So I'm just going to say approximately 100 or 416 million. And this would be via the graph, okay? If I wanted to find the actual population, I would do P is equal to 671 over 1 plus 6.45 e to the negative 0.017 times 140. Okay, so this is T is equal to 140. All right, and then we can do the calculation on our calculator. Okay, but that's not the point. I just wanted to make sure that we were able to look at the function, think about its carrying capacity, and go from there. Okay, and yeah, so in the case where you want to exhibit some exponential growth behavior, but you also want to acknowledge that there are limited resources to support that situation. A logistic function could be just what you need as compared to an exponential function, which assumes there's plentiful resources. So keep this model in mind in conjunction with the exponential models as you're moving through different contexts.